just claim ignorance of the ultraviolet. So I'm not going to put in a Pauli Villars cutoff or anything like that. So explicitly, I just want to show you why the result we got is robust after this renormalization, which is to identify this M renormalized and to redefine the field so that the so-called wave function with renormalization is accomplished. Okay, so the robustness of the result post-renormalization is what I'm trying to get at. And we sort of started down this path last time when we checked that if you take enough derivatives of the self-energy, you are ultraviolet insensitive, or just mathematically, your Feynman integrals are convergent. So let's just start off there again. So, what we saw last time is if you just write, you can do this yourself. If you write sigma as a bunch of diagrams, or a diagram, various terms, you simplify it, you do the traces, you get it. So you write these diagrams, this particular thing. So I will just like that. And it's a function of p squared, then this thing, if you like, has the overall integral. So let me think of it as just one particular diagram for one particular value of q, and then of course you have to sum over all the possible q's that could be going inside that loop. So in this language, you can check check very quickly that b p squared is what I was showing you last time. Okay. So if you never heard of regulators, you never bother to check whether integrals converged or didn't converge. You just write this expression down. Don't look carefully. If you just take two derivatives, it'll hit the integrand, of course. And the result will be ultraviolet finite. And you would never have noticed that there was any problem. Yeah.
So for the first two terms, they're regulated. And you introduce...
First two terms.
Oh, right. This expansion.
I think you're saying it in the sense of some sort of Taylor series,
yeah,
which it is not, which doesn't have.
Okay.
In other words, I'm not necessarily expanding around p squared equals 0. Like I didn't do this. Right. So the logic of it is I'm saying the second derivative is finite, and so therefore sigma can only equal this a plus b where this is the definition of sigma tilde. But the thing that's non-trivial is to say that this is fine.
Quick question.
Yeah.
Why did we know that sigma has been a function of p squared? Is it always a function of p squared?
Well, we saw that, so we see it one shot, that what we've written down is a Lorentz invariant. Right. So in a sense, what you're saying is here, let me give the correct logic. What we're saying is there may be new physics. There may be. So there may be other diagrams. Not, we have done the actual case with Pauli Villars, but just there may be some new stuff that you can virtually afford. It's heavy, you can virtually afford it, and it could come into these diagrams and give you, we assume you get a finite result, of course. Physics is sensible. Hang on. Now, there's no question that what you've written down, if presuming it's finite, there's no question that it is Lorentz invariant. Just look at everything you've written down. This sigma is a scalar function. You can see if G is a scalar function, which it is, two-point correlator of two scalars, and it looks like this. That has to be a scalar. That's got to be a function of p squared. Now, when you wrote this integral down, it didn't immediately, manifestly look like a scalar function. But once you do those integrals, it better turn out to be a scalar function. And you might say, but I can't do those integrals. You're stopping me from doing those integrals because they're divergent. And so I'm saying, whatever the true physics is, so that's let me try to be as clear about the logic as possible. Whatever the true integrand is, we believe it is Lorentz invariant, and this is a function of p squared. Now, what I really want to say is, I don't know what this physics is. It's just whatever it takes to make this finite. I have no idea what it is. But I believe it's heavy. That's my article of faith. I want to test the theory that my theory of psi's and phi's are the only right particles up to vastly heavier scales. Okay, and the heavy scale is up here at some lambda. Okay, so this is the theory that I'm actually testing for the moment, tentatively, right? And if I do that, now when I differentiate, what do I really mean then? I've already said, as an article of faith, of course it's finite. What would I be doing with an infinite theory? So what do I really mean by this? Okay, so let me rephrase what I mean by this. What I mean is that this thing is equal to lambda. Lambda is just the mass scale of new physics beyond my tentative theory of light particles. Okay, it's lambda independent. Plus order 1 over lambda, by which I mean order by dimensional analysis, momenta, physical momenta. This is all I'm saying. And the reason is that this thing, just by itself, if I differentiate under the integral sign, this by itself is convergent. So, under the integral sign, I can do all of those change of variables, this, that, and the other, which put it in a manifest. So with this term in place, I can change integration variables, use the Feynman trick by introducing Feynman x. Feynman trick. Et cetera, till finally I see that sigma, that it's manifestly a function of p squared. Okay, so you can look at all the manipulations I went through, and every time I said, I'm just manipulating infinity here, so it's really cheating. But it wouldn't be cheating if I actually had some sum of diagrams which converge. Then I could do all of these changes of variables, and then life would be good. I'd see it must be a function of p squared, and you'd have it in that sort of Feynman, that nice form using the Feynman trick where it was manifestly a function of p squared. And then you would still say, well, if I don't know about this and I threw it away, it would be divergent. Well, all I'm saying is if you take two derivatives with respect to p squared now, and that's pretty much where I was at the end of last lecture. I had already taken the form in the nicest possible way. Then I took two derivatives with respect to it. And what am I saying? I'm saying that, in fact, just this term by itself already converges. Okay? So that it could only be that this is not a huge part of getting convergence here. It's not that this plus this are conspiring to converge. Can't be, because just by itself this converges. Okay. Furthermore, the contribution of this, if there's convergence, the contribution of this must be going to 0 as lambda goes to infinity, is what I mean here. Why? Because if you just draw this, if you draw any such diagram, I don't care. As soon as you put a heavy propagator, a heavy particle propagator into a theory like this, I don't know the exact Feynman rules, I don't know whether it's got other interactions, but whatever it is, as soon as I have a heavy particle propagator, then naively, the diagram is order 1 over lambda. What could be wrong? Well, there's only one thing that can go wrong. It's order 1 over lambda for fixed loop momenta. Okay? Now that's okay, as long as the integral converges. That means that you're not overwhelmed by large momenta screwing up this counting. Then it's all okay. The whole problem before I differentiated was this did not converge by itself because it needed to diverge to cancel the divergent part of this. Okay. So I couldn't just say, oh look, it's going to have propagators. If it's got any kind of new physics, it's going to have heavy propagators. That's order 1 over lambda. Let's throw it away. That's beneath my error bars. We couldn't say that only because this diverged, hence this must diverge in order for the two to actually converge. Right? So that had to be. But now, after two differentiations, this is convergent. So this better not go around diverging, because it's the sum of the two that better be convergent. Now, given that statement, that it's converging, and the fact that there are heavy propagators somewhere in that picture, I presume there are heavy propagators, to say it's new physics coming in. It is suppressed. It is down. Okay, it is some junk like this. Okay, but only after doing these two differentiations. Now, I gave you the Pauli-Villars thing because it's the quickest thing, kind of a fake new physics, where you can go and check these statements. Keep the Pauli-Villars terms. Differentiate twice. It's not that the Pauli-Villars contribution completely disappears, but you'll see it's just suppressed. Okay? For the dumb reason that all the quadratically divergent piece has been killed by the first derivative, the log divergent piece was killed by the second derivative. That's log lambda, or lambda squared. So then you're left with 1 over lambda. Okay. So that's the true statement here. We often say it very fast. That's why I'm having it out once, so I can speak fast later. Which is, we normally say that if I differentiate the Green's function with respect to external momenta enough times, it's finite. Okay, but the logic of what I'm doing, when I say finite, I really mean insensitive. The word finite or infinite are really code words for sensitive to unknown ultraviolet physics. That's what you mean by infinite. And finite means insensitive to ultraviolet physics that you don't know. Okay? But we speak fast. I don't want to keep saying that. So now when you integrate twice, you end up with the following separation of issues. And this is the whole point of renormalization, and the whole observation is the following. When I integrate twice, I end up getting my Green's function, in this case it's a self-energy diagram, in the form where there is something which is, when I say finite, what I really mean is insensitive lambda insensitive, by which I mean it is equal to lambda. This is precisely, lambda insensitive means you can think of it as something that's independent of lambda, plus things okay. Why? Because it's just the indefinite integral of this statement here, which of course is true. But you have to supplement the indefinite integral with two integration constants. Here they are. Okay. These two things, potentially, all I've checked is this, then potentially they could be lambda dependent and in fact, since we actually put in polyval R's and check, they are lambda dependent. Okay, they better be lambda dependent because we know that the net sigma is lambda dependent. Again, it has to be because this by itself is divergent. So it has to be strongly, the whole thing has to strongly depend on that. So this is strongly, I don't mean like this is sort of a lambda dependence, but who would care? Okay, if there's, say, 10 decimal places between numerator and denominator, who cares? This is strongly lambda dependent. Potentially it is, and in fact, we've seen that in this particular example by calculation, we know that it's strongly lambda dependent. But, so what's the big deal? Who cares? You've taken something and you've separated it into saying there's something which is insensitive to lambda, there's something sensitive to lambda, but I've got the sum of the two, so what have I learned? It's this. But it is polynomial in P, the external momentum. Okay, so this turns out to be the critical separation. The reason I was complaining about saying just do a Taylor series, I don't want to think of what I'm doing here as a Taylor series, is this function here, which has things like log of p squared and blah, 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 might not be analytic enough to do a Taylor expansion. Okay. Now, when it's polynomial in external momentum, that corresponds, after your Fourier transform, to local in X mu space. Okay? Like this just looks like the D'Alembert when you Fourier transform p squared, it's just the D'Alembert. So that sitting in something like this p squared looks very much like the D'Alembertian, the inverse of the D'Alembertian that gave rise to the propagator in the first place. This constant term looks very much like the m squared that you were putting in. In other words, these are things that came out of an action, which is a local action. Okay, local meaning it's the integral of things that only depend on the point x and infinitesimally close to x. And we will see, I don't want to overload you now, that it's the polynomiality of the ultraviolet divergences which tame them, which say that we can just take pre-existing contributions to our Green's function and just renormalize them, by which we mean just absorb these divergences into redefinitions of our input parameters, like this m squared. And then the sensitivity to them is gone. And since these terms were already things that we expected to be inputs to our calculation, the fact that we now have to go and fit to renormalize parameters means that we were no worse off for having seen these divergences. Now, that's a little bit of a long story. I'm just previewing what's to come. But let me at least say that it was non-trivial. The separation I'm doing is non-trivial precisely because this is a totally general function. I don't know how many parameters it is, and so on and so on. How do you fact that I have managed to take just two constants, which contain all of the strong dependence on physics that I don't know, is a huge achievement. Okay? And that's the point. That means that even if I don't know them, they're finite. They're finite in the world, in the language in which I think of lambda as there. So the only problem is they're very sensitive to this new physics. I don't know what that new physics is, but I have an experimental trick. Measure A and B and get on with the rest of life. That's it, okay? I can predict an infinite number of numbers, otherwise known as a function, by simply measuring two constants. That's the game plan. So this is sort of where we were last time. And what I want to show, now that we've settled what I mean by these terms, is that general structure. See, I haven't redone Pauli-Villars in any way here. I've taken some general new physics, and I just want to show you that structure that we got last time, it's not a coincidence, it was just something that had to happen on general terms.
Can I ask a quick question about A and B?
Yeah.
So you said they're lambda dependent and that you could go out and measure them.
Yeah.
But you could also subtract some number off of them and put it into sigma.
Yeah, good point. So, just as a matter of calculus, here I'm going from this line to this line by integrating. From here to here is a indefinite integral, okay? And so, just how much you put in the subtraction constants, or sorry, these integration constants, how much I put in the integration constants and how much I put here is my choice. For example, I could put 1 plus b here. I could change my b to 1 plus b and just put minus p squared here. Now, it is still true that this is, if this was lambda insensitive, this is just as lambda insensitive. And this is still just two numbers which, if this was lambda sensitive, then 1 plus something I don't know is also something I don't know. So, there's an arbitrariness there. And indeed, this will come into what is meant. This arbitrariness, you can fix it however you want. You see, just as long as you and I agree on our convention for how much to include in this and how much to include in this, we're good to go. And we can, once we agree on a convention, and this is called a renormalization scheme, which we will get to, then we will go fit these things and move on. And we'll see a kind of a scheme pretty soon, because it might be confusing, you see. I have the data, I have this, I can clearly, how could I possibly fit B? How could I possibly fit B if I could have just as well managed to pull out the number B plus 1? Okay. So we'll see how you can sort of make a choice unambiguously so that you can actually fit data by some absolute prescription. But just to say one quickly, you could, for example, the kind of condition that often is used, it would be, suppose I said that sigma tilde at, suppose I define that sigma tilde at some random scale, which I'll call mu, equals 0. Suppose I said that. Now, maybe my original thing, I chose an indefinite integral choice, where if I just plug in mu squared, it's not 0. Oh no, what am I going to do? Well, I might just subtract, I might just put something here, c plus b, and here minus c p squared, like this. And now this new sigma tilde satisfies that. That's what I mean by condition, you see, and then that would fix it. We'd all fit to the same type of parameterization. This is a renormalization condition. This is an example of what's called a renormalization scale, or a renormalization point. But it's not that deep. We just have an indefinite integral, and we have to figure out how to do it. But turns out that we get a lot of mileage from this. You can almost turn this into a symmetry, you see. The fact that you can add a little bit here and subtract a little bit here. becomes a symmetry, and it turns it to be the root of what is called the renormalization group. It's not quite a symmetry, I forget what it's called, but it's close enough to a symmetry. Okay, it's a kind of a, free information is hard to come by non-perturbatively. And this little observation that you can shift things around is a kind of a free and non-perturbative insight. So we'll see a little later at least some of the roots of that story. Okay, so let's see what would, as I said, let's just redo what we did last time in 5 minutes. And so if we're trying to calculate, as we were, so I'll just say it very quickly, phi okay, this is what the Green's function is. And suppose I call it phi old, meaning this is whatever you walked in the room with, telling me to calculate before you ever saw a divergence or any subtlety. But suppose instead I calculate phi nu, where phi nu is equal to root z phi old. Okay? We already have seen why I would do such a thing from the Pauli-Villars case, but let's just do it in general. Somebody says, I don't like your choice of field variable. I want to change it by some amount root z. Okay, then instead of calculating phi old, I perhaps calculate this. I know how to go back and forth, so what's the problem? Okay, so let's just calculate this instead. And so at tree level, you'd say this is equal to iz that is, it's z times bigger than what we know was the previous answer. That would be a tree level, the simple story. I just want to write this as p squared over z, m squared over z. Okay? But I don't want to do tree level. I want to do this one loop self-energy thing, which you can think of as now, we know this is not quite the right way to think of it, but mnemonically, the correct answer is really the sum of this geometric series, which is so I'm not repeating all this philosophical statement which says that the sigma first came to it, never thought about anything, you would do this. Then, once you're more enlightened, you'd say, no, it's as if I just resummed the series, even in when p squared is close to unshelled, where I would be outside the domain of convergence of the series. But the answer would look like this. And in fact, this is the right way to think. Okay, so I'm not repeating that part of the philosophy. But now, I just want to rewrite it using this business. So, indeed, I'm using
possible.
Okay, and so this, we know that this A and the B are very sensitive to new physics. Panic. Okay, what do I do? Well, I'm just going to say, I'm going to get rid of B dependence, and hence the high energy dependence of B, by declaring that this is 1. How? By choice of Z. I will just solve this equation equals 1 for Z, and it'll tell me that by choosing Z appropriately, I could just make this number 1. Okay, so I will just choose to use the field variables in which I never see this effect. You might say, gosh, but if I don't know how the change of variables occurred, how will I ever reconstruct whatever it is I wanted? Well, as we will see in what's coming, you wanted the S matrix, say, okay? You don't know what field normalization you use, okay? But so there's no preferred choice. Not like this was the God-given thing you were supposed to use. But so this is really truly a convention. Choose whatever you want. You can make it 5. You can make it whatever you want. But anyway, let me start with this first pass. Let's see what to do. And this thing, I'm just defining as m squared normalized. Again, I'll just choose my m squared. Having chosen my z already by this equation equals 1, I will choose my little m squared so that this whole thing is given by some finite thing I call m squared normalized. The right way to think, of course, is I'm just writing it like this and like this, especially this one is, I hope, the clearest. I'm not planning to calculate this or worry about the cutoff dependence in here or the new physics dependence in here. I'm just planning to measure this and that's it. Just fit it to the data. And so this is equal to I p squared minus m squared normalized minus sigma tilde p squared plus I epsilon. And this is sort of lambda independent. And this thing fit to data. Note, I said this before, this is not the physical mass in general. This is not the pole of this propagator. But all I'm trying to show you right now is that I have an expression which is at least finite or ultraviolet insensitive, and 2, it has the same number of unknowns from a pure theorist point of view. It has the same number of unknowns as I thought I would have had anyway. Even if I'm a tree level guy and I wrote down this, I can't do any business with this till somebody tells me that m squared. Hopefully I just measure it in data. Even at tree level, I knew I had to do that. I'm no worse off. I need this m squared normalized. Somebody just has to tell me what it is. I can just measure it from the data. Everything else is, so of course hidden in here is m, but you also thought you had to measure that. You also thought you needed g, and you still need g. So you're not any worse off by having seen these frightening things. Okay, so that's the finite part.
How did you get rid of the lambda dependence? Z is now lambda dependent.
Yeah, so the z is lambda dependent. The real question is, so let me say there's sort of two sensitive places, A done is we've agreed to not go around calculating phi old, phi old. We're going to see, can we continue to do business by just calculating phi new correlators. And so the difference between the two is got this z, and if you solve this equation for equals 1, that means that the z, since B is new physics dependent, or let me just call it ultraviolet sensitive, therefore Z is ultraviolet sensitive. So what I'm now seeing is I don't know, given this, whatever your phi old was, I don't know how much I rescaled it to get this. But because the amount that I rescaled it by is ultraviolet sensitive, and I don't know that ultraviolet physics. But on the other hand, I could just walk in the door and say, I'm just going to think in terms of this variable. And so, to some extent, we're trying to see, maybe I don't care what this phi old was, in which case I don't need to know how much rescaling had to be done. I just need to know that such a rescaling exists, which we see it exists. Okay. Now this one is maybe tighter. It's saying, no, it's not just your convention for what you want to talk about, that's the dynamical variable. Here too, there is lambda dependence inside A. If you do that Pauli-Villars calculation and figure out who we want to call A, it sure has Pauli-Villars dependence in it. And more generally, therefore, by this argument on the far left, it has new physics sensitivity. This little m squared, if you want to get this and this and this to equal this, then you will definitely, so little m squared, let's just solve this one. 1 over z minus b equals 1. So this is equal to b plus 1. Z is equal to 1 over 1 plus b. Okay? B is got log lambda inside it. So yeah, this is very sensitive to lambda. Right? If lambda goes to infinity, z actually goes to 0. Bizarre. Okay? This thing here, let's just solve that one. It says that m squared over z plus a is equal to m squared. See, what we're really doing here, we're shifting the symbols around, but what I'm really doing is changing who is the dependent and who is the independent variable. If you remember your thermodynamics, which I don't, you will remember that you're like constantly figuring out which is the dependent, which is the independent. Well, and we're going to do more of that. And that's what's happening here. So really, let me redo it. I'm now taking this as the independent variable. You see, when you say, well, oh yeah, you just gave a name to this bunch of infinities over here, or this bunch of things I don't know. That doesn't make me know it anymore. But I'm saying, no, this is the input parameter of your theory. Think of it that way. Because it's the kind of thing you can imagine going and measuring. Okay. But just to point out that you're right, that it is sort of infinite. So then I can take the minus a here. And so one way of thinking is, I'm taking my little m squared. Nobody told me who little m squared was in the first place. But if I take it to be this input parameter m squared renormalized, and subtract this infinite quantity and then multiply by this other infinite quantity, UV sensitive quantity, then by magic I'll get this amazing cancellation and I'll get a finite result, m squared renormalized. Okay. But what you're really noting is, I think the way I said it originally, this is the way it's often phrased, you know, let us contrive to choose an initial so-called bare mass where it is chosen in exactly this way in terms of some finite quantity that is your real input parameter. And that way, all the infinities will cancel here, by design. Okay. I think the right way to say it is exactly the way I first said it here. the right way to say it is, yes, this is, I'm not saying this is not insensitive. I'm not saying A is insensitive, it's sensitive. I'm not saying that Z is insensitive in this sense. It's sensitive to the ultraviolet physics, I don't know. And I'm just saying, you know, you're measuring it, that's all. But once you've measured it, you don't need to measure it again and again. I mean, once you've measured it, it's a little, it sits there, and then I no longer am lacking information about the ultraviolet. That's all. The far ultraviolet has been sort of factored into this one quantity. Truly, it is there. If you want, that's what I'm saying. It truly is there, but we just go measure it. Okay. It's not gone in any sense, but it looks gone by just giving it this name.
So are you saying little n is lambda dependent? And
Yeah, when you write this in terms, so when you actually say I'm choosing this formally, as opposed to the way I just said it, which is, look, I don't care what you just take everything the way it was given to you, go measure this guy, and you're done. But if you want to say it formally, which is often the sort of textbook way to talk, you would say, a priori, I start with m squared being an input parameter. It is the independent variable, and everything is dependent on it. Of course, just like every other coupling in mass that was in the Lagrangian, everything is an output that is a function of this thing. I am formally going to change that. I'm going to trade m squared as the input parameter, and I'm going to make it, rather than an independent variable, I'm going to make it a dependent variable, and this is going to be my independent variable. In which case, I write it like this. Okay? And then you would say exactly what you said. If this is my independent variable, I'm choosing this variable to be cutoff dependent, or new physics sensitive in this exact way. And I'm choosing it in exactly this way, so that this combination magically has all cutoff dependence or UV sensitivity canceling out. It is a formal statement, but this formal statement, I hate formal statements, but because they're too easily digested without thinking them through. So probably at this point, the best thing to do is to think it through. The formal statement is the thing that comes at the end of your physical intuition, not, unfortunately, in some textbook presentation. I am going to make this the dependent variable. This is the independent variable. See, now the problems are gone. Okay. The Gedanken experiment is the clearest way of thinking. So go away and think like that. Let me know if there's confusion. Yes.
Sorry, go ahead.
So you could easily have chosen Z such that the coefficient in front of p square vanishes, but then the tree level would be meaningless in that sense. So,
yeah, let's see. There's a, the other restriction that we have is that we should have been doing, let me try and recover it in this case, but we saw it in the Pauli-Villar's case, we saw, it's not like all the expressions completely turned into this nice finite expression. We actually had to throw away higher order stuff.
yes.
Right? And so let me see if I can do it. But I believe the answer to your question is, if I were to attempt to say, well, why not make it 0? If I redo this thing, I will see I'm not doing perturbation theory anymore. That is, but let me, so that's my quick statement. Let me see if I can spot it. Yes, in the following sense. So B is equal to, so B is order G squared formally. There may be cutoffs, this, that, and that. I mean, there may be lambda dependence, but this definitely is. In fact, let me be even a little more explicit. It's something like, okay, be sloppy. And So now you say, I want Z to equal, I want Z
1 by b.
to be 1 over b, which is, so I want Z to be 1 over g squared log lambda. Okay. And yet, my tree levels, suppose we do the entire exercise at tree level. The entire exercise. At tree level, everything works out fairly straightforwardly. The Z is 1. Right? So, Z at tree level is 1. Z at this one loop level is this 1 over g squared. But I'm expecting everything to be, I'm believing I'm doing perturbation theory. I am doing perturbation theory. And so everything should look like something Z naught plus g squared, Z1 plus g to the 4th, Z2. And in fact, when we learn the generality, the general way of renormalizing, indeed we will be doing it like this. Everything is perturbative. Right? Your thing is not. You're making some drastic big move at one loop level, which I am not. You see, that's 1 plus what did you say? I'm trying to guess what physical thing might be bothering you. But, well, think further, let me know. But let me just, I feel I'm speaking a bit too legalistically, but I think this is the underlying problem. That you would be making a drastic change of the theory at one loop, rather than just saying, oh, everything is perturbative. That would be the problem.
I just had a quick question about fixing your scheme, like you said before.
Yeah.
How did I want to phrase this? In practice, what you would do is you get some prediction perturbatively for sigma, and it's like ambiguous up to sort of some polynomial in A plus B. So there's a lot of, so your perturbative calculation, you have a lot of information in there with like the log dependence and that sort of thing.
Right.
And so, let's see, what was my question? I'm sorry, that wasn't my question. I had a question, but it just went away. Oh, no, yeah, my question was, is it really all you have to do is you just like fix a value of, fix what sigma is at one value, and then in general that would work, or?
Yeah. Typically, the number of integration constants you have will require you to stipulate a certain number of conditions on this.
Okay, but then everywhere else you get.
And then everywhere else, it's just like if somebody says, the derivative of function is x. Then I say, okay, I know x. I know f. It's x squared over 2 plus a constant. Now, if I happen to tell you that f of 1 is equal to 0, then certainly I know f of x everywhere else. You see?
Okay.
That's exactly it.
Okay. So.
Okay, so this is how we've got back to something finite. And now, you know, there is a series of things you keep learning in field theory where you keep coming back to the S matrix. Okay? So, I'm assuming that everybody has been exposed to, both non-relativistically and in the relativistic case, to the idea of the S matrix, and in particular that you've got the sort of tree-level S matrix under your belt. So you had to calculate a tree-level S matrix element and hand it to an experimenter and tell them, go check whether this is right, that you know how to do it. And in field theory, one of the jobs is, as you learn anything, just to know whether we are talking about something concrete or we're philosophizing about unmeasurable things. The job is always to bring it back to the S matrix and say, well, how did it change my view of the S matrix? And so that's what we're about to do. Okay, we're saying, where did all this end up again? Well, at least one thing, well, we're going to keep answering this for a few lectures, but at least one thing is to see where it makes a difference to the S matrix. And what you see with the case of the S matrix is the general idea of the S matrix, you keep on amending it and correcting it to include subtler and subtler situations. And we'll see right now that this is, these loops provide, and in particular self-energy provides a kind of a subtlety that at first sight you might not have anticipated when you constructed the tree-level S matrix. So of course, intuitively, if you give me a bunch of, we think of the S matrix as a kind of glorified matrix in where the matrix element, the matrix indices are collections of incoming momenta of free particles and collections of outgoing momenta of free particles. And then the S matrix is supposed to be the amplitude for one starting very early to evolve into the other at very late times. Okay, I'm not saying this in minute detail, but the idea is that it's something like t early goes to minus infinity and t late goes to infinity, and I'll put this in inverted commas, that is whatever stipulations and provisos and blah 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 you're used to, they're still there. I'm just reminding you of the spirit of the S matrix. And the instinct, which we have to keep gauging every time we construct the S matrix at a greater level of sophistication, the instinct is that all the interactions happen in some central region of space-time. And so at very early times, all the particles have are very far apart and non-interacting. Even though the interactions are there, they just don't have anybody to interact with in their vicinity. And then even after the scattering has happened, particles fly out of this interaction region, get very far apart from each other, and again cease to interact with each other, so that these are really free momenta. And of course, since they're going on forever and ever, they're on shell. Okay. There's something called the transition matrix, which is, if there were no interactions at all, then the S matrix, or S operator, perhaps would be better, since this is sort of free Hilbert space. So it's really an operator, Hilbert space. But this S matrix, if the theory was just a free theory, then what came in better be what came out. So you would just have the S matrix equals the identity matrix. Okay? Which means the same number of particles in and out, and every particle in should have the same momentum as the particle coming out. That's what I mean by the identity. Okay? But in general, it's not an interacting theory, and so I have to add some correction. And if we're thinking vaguely perturbatively, then we say, well, this is at least the first approximation, or the 0th approximation, and so it's worth giving a name to the next thing, and that's it, which is everything else. So there's nothing and everything else that could possibly happen. Okay. The I is by convention, and this is the so-called transition matrix. And this thing itself is written in Paschinian language, I guess, I don't know, I suppose it's everybody calls it. It's written like this, but with the overall momentum conservation delta function refinement diagrams. There's always one delta function overall that you can't get rid of, and that's the one that enforces the overall momentum conservation. The sum of these momenta has to be the sum of these momenta. Okay, schematically, that's it. And so this thing that is picked out, this M, curly M, is just, so Peskin calls it, presumably he's right, it's just called the matrix element.